Okay, coming back from break, we're going to go ahead and continue on with our G10 lines for outputting tool offset info. Okay, P G10 TLOFF tool offset write buffer. This is actually going to be buffer number 3 here. So buffer 3 works the preload buffer. So first thing we get, we reset our test condition, and we set size 3 equal to the size of the buffer. So we read record number 0. Now, typically when I go through this, okay, so we're not using test there. Let's search for test, and let's make sure that it's initialized. See, there's test 2. So, again, test 2 equals 0, test 2, test 2. So, what we're going to do is we're going to call this test 3. And we're going to search throughout this logic to find all the instances of test 3. And we're going to modify it like this. So we also need to make sure that we have a test 3 variable defined. So I'm going to go find size 3. And we're going to initialize test 3. Okay, so size 3, size 3, size 3, size 3. So test 3 equals 0. Size 3 equals rbuff 3. I'm replacing the numbers here with the constant values because I think it's just a cleaner way to do it. So, while RC3 is less than or equal to size 3, you notice offset 3 equals read buffer. We're going to read from buffer number 3, and we're going to use the value of RC3. So keep in mind that RC3, if we go search for it, was initialized to 1. So let's go back here to our write buffer. So it's always going to start out as 1, and in fact, you'll see down below here, reset read counter for next pass. We always reset it to 1 at the end here. So it should always start out at 1. And size 3 should always hold the actual size of our buffer. So when we first start this loop, while 1, so that value is going to be 1, is less than or equal to, say, 10, say if there were 10 records in here, we would jump into this block. Now we read all the values. In this case, this buffer only holds 1 numeric value at a time. So we read from buffer number 3 using RC3 as our counter variable. So it should start at 1. We're going to load that tool value into offset 3. Now, the next statement is from V9, so it says if tool off number. We need to add a $sign to that. So if the tool offset number equals offset 3, test 3 equals 1. So if the current tool offset number is equal to the offset number that we've read from the buffer, we're setting test 3 equal to 1. So you can see down here, now we check to see if test 3 equals 0. So if test 3 equals 0, it was not found in the buffer, because we loop through, this while loop loops through the entire buffer, no matter how big or small it is, and checks every value in the buffer against the current value of tool offset. And if it's found, we set that flag. And then we check the flag. If test 3 equals 0, so it has not been written yet, offset 3 equals tool offset number, and then offset 3 gets written to the buffer. And finally, at the very end, we reset the read counter for the next pass. So we set RC3 back to 1. This is all there is to write to the buffer. So this, again, first reads from the buffer to make sure that we're not writing a duplicate, and then writes to the buffer if we aren't writing a duplicate. Any questions about how we're writing to the buffer or about what this does right here? Good. Okay. So again, this is just where we write. We do some reading here just to be sure that we're not writing duplicate values. But the ultimate goal here is every time we encounter a new tool number, we check through the buffer to see if that tool number has been written. And if it has not been written, we write it to the buffer. That's it. So that is the preload for writing the buffer. So now we want something like this. If use G10 tool offset equals yes, preload tool off. We're going to go ahead and turn our switch variable to yes. And let's go look at the output. This is the post block that gets called. So we're going to call this in right at the beginning of psof, right at the start of the file, because that's where we want to output this tool offset and tool origin data using these G10 lines. So you notice it says this post block is called from the psof and peof post blocks, and only if the use G10 tool offset flag is on. This post block is responsible for reading the tool offset buffer and outputting the preloads or cancel to the NC output file. So the first thing that we hit in preload TLOFF, so preload tool offsets, is PG10 sort L12. Now, I hate this post block name. Can anybody guess why I would dislike that post block name? Yes, L and 1 look the same. Thank you, Bill. I hate this right here. I think it would have been much better if they had used a capital L, or had they called this, tools or something like that. PG set, G10 sort L12. looks terrible. Just from a reading perspective. Now, I'm not going to necessarily go and change it because really it gets called, here's the call and here's the sort routine. That's it. So literally it gets called one time, it gets called here. If I had to call this from multiple places, you can bet your butt that I would change that to something that is more readable and less error prone. But for now, it's okay. All right, so the first thing we do is we sort the data. So let's go look at that. Pre-sort L12. Sort preload work offsets in ascending order. This post block is designed to sort the tool offset preload buffer in ascending order. This post block is called from the preload TLOFF, preload tool offset post block. Do not modify this post block unless you're absolutely sure of what you are doing. Okay, so fortunately we also have myself who kind of knows what he's doing, and we're going to explore how this whole thing works. I am going back through here and replacing all of the literal numerical values with the constant values. And I do that because, number one, it helps processing, and I think it also helps readability, especially when you've got lots of these numbers going on. Okay. Counts. We've already got some variables initialized, and so what I did was I took CNT1 and I just added the OU because I like being able to read this more like a sentence. I think it helps figure the whole thing out. So what we're going to do is we're just going to do a find and replace. So I'm going to do a replace on CNT1 with COUNT, or excuse me, CNT2 with COUNT2. Replace all those, and we're going to replace CNT1 with COUNT1. Replace all. Okay. Save that. Now, what happens at the top here? We set our read counter 3 variable to 1, and we get the size of buffer number 3. So we read buff size number, buffer number 3, and we read record number 0, which always gives us the size. Now, we initialize our counters, so we set count 1 and count 2 to be the same. The next section, just like we looked at last week for the other buffer, has a nested while loop. While. Let me make sure all this stuff is lined up right. What we are doing here, I'll see if I can explain this in kind of out loud. What this whole mechanism right here does. We read the buffer starting with record number 1 and record number 2. We compare record number 1 and record number 2. If record 1 is greater than 2, we swap them. And we start out with 1, 2, and we compare 1 and 2. Then we compare 2 and 3. Then we compare 3 and 4. Then 4 and 5, then 5 and 6, and so on. And this mechanism here sorts the data. Okay, so while count 1 is less than size 3. So remember, count 1 starts off at 1. And size 3 is going to be the size of our buffer. So we get the actual size of a buffer. Let's put some real numbers in here. Okay? Let's say that size 3 was 6. And count 1 is always going to start out 1. So while 1 is less than 6, we jump in here. Excuse me. We set size 3 equal to, we're going to read the buffer again. So we're going to get the size of the buffer. While count 2 is less than or equal to size 3 minus count 1. So it says loop number 2, loop 1 less every time. RC3 equals count 2. Set buffer read counter to the current loop counter value, current record to read. Offset 3 equals read buff 3 RC3. Offset n equals read buff 3 RC3. What we do, we always read an array of values. Buffer number 3, the array happens to only hold one value in the array, but that's okay. So let's say that we start out with RC3 equal to 1. When we first jump in here, everything's equal to 1 because count 2 is equal to 1, RC3 is going to be equal to 1. So what we're doing here is setting offset 3 equal to the first record in the array. First record. Then we set offset n equal to the second record. The reason I know it's the second record is that RC3 gets auto incremented every time we use it. Okay, so we start out with it set to 1. Now this is going to be record number 1. This is going to be record number 2. So we read the first 2 records from the array. If offset n is less than offset 3, we swap the records. Okay, so if the next, so this offset n should be the second record at this point. Offset 3 should be the first record. So if offset n is greater, then we set the right counter equal to the current value of count 2. In this case, it's 1. And we take offset n. Remember, this was the second value. We take offset n and we write it to the buffer. Then we take offset 3 and we write it to the buffer next. So this is where we swap those values. Okay? And now we say count 2 equals count 2 plus 1. So now in this while loop, we have just incremented count 2 by 1. So now we go and we repeat this. Okay? So we go back up and we check count 2. It was 1, right? Now it is 2 because we've just incremented it. So it says while 2 is less than or equal to size 3 minus count 1. Now we jump back in here. Okay, we set RC3 equal to count 2. So this should now be 2. All right, this is the next loop into our buffer. Since this is now 2, offset 3 is going to be equal to the second record in our buffer. Since RC3 now gets auto-incremented, offset n now is going to be equal to the third record in our buffer. So now we're checking 2 and we're checking 3. So this will be equal to number 2. This will be equal to number 3. We check and see if their values need to be swapped. If they need to be swapped, we do. If not, we ignore that and we increment the counter again. So this literally will compare records 1 and 2, then 2 and 3, then 3 and 4, then 4 and 5, then 5 and 6, and so on until we've looped all the way through the buffer to sort it. After we complete an entire loop through the whole buffer. We set count 2 equal to 1, and we set count 1 equal to count 1 plus 1. So we increment count 1. And then we come all the way back up and we repeat this whole process again. So this nested while loop with different count variables to set the controls is a very sophisticated mechanism in MP, because it allows you to go and sort values in a buffer. Does anybody have any questions about what we're doing here with this nested while loop to sort the data? Good. No questions is good. Okay. So let's just make sure that we got everything set up here. We want to make sure we replace all of these values with their constant counterparts, just because it's cleaner that way. Let's line this stuff up, make it a little bit cleaner here. Oh, didn't want to do that. Okay. All right. So again, this is going to sort our data. Now that we've completed sorting it, we're going to set our read counter equal to 1. And we're going to get the size of our buffer. So we're going to read record 0. And then we're going to loop through and output values from our buffer. So while RC3 less than or equal to size 3, we set offset 3 from the buffer. So remember, we start out at 1. Offset 3 equals read buffer. We're going to read buffer number 3. And we're going to start reading at the first value. And all we're going to do is format this for output. So in this case, we've got PBLD and $. We're going to force the string selector for sgabzinc. Then we're going to output G10, L12. We're going to force out offset number 3. And remember, we set offset 3 from the buffer. So we're going to force out, that's basically the tool number value. Then we're going to output R0. And then we've got our $. Okay, so let's look at what that output there looks like. Make sure, check PSOF real quick. Preload tool offsets. Okay. Let's do this one. Okay, and here we're getting all of the L12 values for the tools that we want to load, and they are sorted in ascending order. If we didn't want to sort them, we could do what we did with the work offset, and we could add a condition here to say do you want to sort the G10 lines for the tools? So let's just look at that real quick. I think that's probably a valuable addition. And I think we can actually use this for both. I think we say if sort G10, we can call pg10 sort L12. Again, I really dislike the sort L12, but consider we only use it once in this post. I think we'll live with it. Okay, so if we turn the sorting off, oh, yeah, 239, 234, 229, 245, and now we go back in there and say yes. And we repost. $229, $234, $238, $239, $245, $213. So, yeah. Now we do need to look into why the mapping isn't working. But I can leave that set to no for now, and we should. Let's just do this one. This one's fine. Okay, now we should get it in order, and we're using the values direct from the dialog. Okay. Let's go back to the MP documentation and just see if there's anything that we still have to cover in here. Okay. Just as kind of an overview, again, we're going to go through this. Buffer files that you can use the MP language to store and retrieve data. They are temporary in general, right? We know that. We have a way to save those files out, either for debugging, which is certainly one way that we could use it, or because we actually want to use the file as a mechanism for output. Mastercam has several different auxiliary files. There's actually an auxiliary file, a sub file, an ext file. So there are basically besides the NC file, there are 4 additional what you can think of as sub-program files that have some things built around them. But for some people, that's not enough. And the other problem is you can't just hijack the sub file or the aux file or the ext file without interfering with existing mechanisms that may use those files. So using a buffer file is a great way to give you the ability to output and have control over up to 10 additional files for MP. So again, they are a place to store temporary data. a way of entering data that cannot be entered using an NCI file, and a way of outputting data other than to the NC file or the other auxiliary or additional files that Mastercam or that MP has control over. There are two kinds of buffer files: string buffers and real number buffers. String buffers look like a spreadsheet with one column and unlimited rows. The width of this column used to be fixed. It used to be you could only have 80 characters. Ever since Mastercam X came along, the character limit is now set to whatever the max path length is, which is a Windows API setting. So typically that's going to be something like 2048. So typically you could have, probably practically, you could have about up to 2,000 characters on a single line. And again, a buffer is generally unlimited. It is allowed to grow vertically. A good practical limit here is either 128 or 256 characters. It's going to be pretty rare for you to, to have over 256 characters of data per line. I have seen some that go out pretty wide. Now, as you get into building string buffers, this doesn't really have to do with buffers themselves per se, but if you do string concatenation, okay, if you start getting into doing string concatenation and you start adding up a bunch of string variables together, there is a limit on the width of that line in MP. So I believe it is something like 248 or 256 characters, somewhere right around there. So even if you do this, even if you have a string like this and you decide, hey, I want to continue that string on another line, that is perfectly acceptable. But at some point in the background, MP is going to be adding up all of these strings together, and there is a physical limit to the number of characters that you can have total in the string that you're building. And like I said, it's 200 and something, like 230 or 248 or something like that. Anyway, just a heads up that you want to think about your variable names and not make them too short and not make them too long. You want to make them descriptive enough that you can figure out what's going on, and you want to follow some best practices, right? But just keep this in mind. Just a word to the wise, okay? So, string buffers, one column of data, unlimited rows. Real number buffers, unlimited rows, and multiple columns, anywhere from 1 to as many columns as you specify. Let's go look again, just as a review, at MP LFan. Oh, not mill, lathe, and posts. I'll just choose MP LFan. If I look at buffer number 1, fbuff 1 0 28 0 0. This buffer has 28 numeric variables per row. Each record stores or retrieves 28 pieces of data. I'll set a bookmark. If we look near the top of this buffer, we have our standard kind of variables, WC1, RC1. So the write counter 1, the read counter 1, and then we have NC1. And you'll notice that NC1 is initialized to a value of 2. NC1 is used as the next variable counter. What we do with buffer 1 in this particular post is write records that contain all of this different data for each tool change, whether it is a null tool change or whether it is an actual tool change or whether it is the start of file. If we look at this list and we count down this list, there are 28 variables. If we look at the next tool information list and we start at this variable and we count down, there are 28 variables. There is nothing that explicitly ties this variable list to this buffer. That's an important idea to hold in your head, because this buffer has to use a list of 28 variables to read and write from. But nothing says these variables are explicitly part of this buffer. You could have 10 different lists of 28 variables if you wanted to. And by using the proper read and write counter, you could store 10 different blocks of data, each block of data containing 28 different variables. So that I wanted to point that out, that these variable lists are important because you need a list of at least 28 variables to read and write from. But there's nothing that explicitly associates these two together, this statement and these variables, besides the wbuff and rbuff commands. So the read buffer and the write buffer. Okay, let's look at how we populate this data. If I go look at pwrtt, this is the start of the tool change. Where is it called? Well, when the tool table variable is turned on, it is called at each tool change event during the NCI pre-read loop. So what we're doing here is setting a bunch of values. So if G-code equals 1001, we call P setup. Then we call P cut CC type. We set the value of CC pause. if G code is not equal to 1001, we call P last record. This one here, P current record, is where we actually write the buffer data. So if I look at P current, PCUR underscore RECD, write to the current tool record. If we look at this entire post block, I don't even think I can get the whole thing on the screen. Come on. Let's see if I can. There. Almost. We can almost get the whole line, or the whole post block, in the window. This is the only line that actually writes data to the buffer. If you look above that line, from here all the way up to here, all of these pieces are only responsible for setting values that we are going to write. So let's look up at the top here. C1 G code equals G code $. P matrix setup, P matrix underscore SU, P set underscore turret, and P map home. Calculate values based on whatever data is being presented to those post blocks. After we set the G code value, next we set the home values. Look at this line of code right here, highlighted in yellow. C1 underscore XH equals VEQU X abs. What's going on here? What does that line of code do? Any guesses? It does. It sets XYZ in abs, but here's what it sets. It sets the value of C1 underscore XH, C1 underscore YH, and C1 underscore ZH. And it sets those values from the values of X abs, Y abs, and Z abs. X abs holds a value. It holds an absolute position that was calculated in one of these post blocks, I think in P matrix setup. This vector equate, this single line here, sets three values. It sets C1 underscore XH, C1 underscore YH, and C1 underscore ZH. So with one line of code, because we're using a vector math function, it's actually able to copy an implied array starting with X abs into an implied array starting with C1 XH. So here we've set 3 values. What about this next line? C1 underscore TOX equals VMAP TOX $, comma, MMTX1. This is another vector math function. And this vector math function also works with 3 values. It maps the value of TOX, it maps the value of TOY, and it maps the value of TOZ into this matrix, and it sets the resulting values into C1 underscore TOX, C1 underscore TOY, and C1 underscore TOZ. The important thing to notice here is that with 2 lines of code, we have set 6 different variable values. Now we set the value of CC pause. This is just a straight equation, okay? C1 underscore CC pause equals CC pause $. The next 2 lines of code are an if-else statement. What is the result of that if-else statement? The result is we set the value of C1 tool. The next 3 are pretty self-explanatory because they're just, again, straight up equations. You know, this one equals this one equals this one equals the absolute value of SS, okay? But still, we've got 1, 2, 3, 4, 5, 6, 7, 8. So these 2 lines set our 8th variable. 9, 10, 11. Okay, so by the time we hit this spot right here, we've set 11 different variable values. Okay, so now we're at 11. Now we have another if-else. That's 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and are in here. So we would have to look and see, you know, I don't see us setting any more C1 values in here. But I think if you look back at pwrtt, we may be setting some of the values here before we write it. Okay, so this is the important part to understand, is that if we're using an array that has 28 values in it, we have to set all 28 of those values before we call this single line of code. Okay, so, you know, again, and then it looks like some values are also set in pcut cc type. So some of those values that we need to write may also be set here before we actually end up calling this single line of code. This is where the magic happens as far as getting those values into the buffer. All right? So, like I said, this one here is all about writing those values to the buffer. Pcut cc type, p setup, and if we go rbuff, So here, P last record, okay, it says update the last records for min, max, and point. RC1 equals WC1 minus 1. C1 G code equals RBUF1 RC1. So we just read 28 values from the buffer with this line of code. If previous opcode is not equal to 104, now we set. So here's what we're doing is we're reading the current line. We are looking and making sure that previous opcode is not 104, and we are setting C1 X min equal to X min and C1 X max equal to X underscore max. And then you'll notice RC1 equals WC1 minus 1. C1 G code equals WBUF1 RC1. We are writing back to the buffer after we have manipulated two of these values. This is a tricky, sneaky move, okay, what we're doing here, because we're reading in a value and we're then going back in and we are only modifying two of the values that are in out of those 28. And then we are writing the entire line back to the buffer with these newly modified values. Why are we doing that? Anybody got a guess? Like, why would we need this right here? You said, Craig says, just to update. Kind of. Here's the deal. When we go to write data to the buffer at the tool change, we don't know anything about what's coming up in the operation. That's not the way that the NCI processes. The NCI processes 2 lines at a time, right? So it reads like a script. We start at the beginning of the act and we keep on going through till the end. We can't really jump ahead. So what ends up happening when we're writing min and max values, we actually have to get all the way through the operation before we know what the X min and the X max are. So this allows us to go kind of to the end of the operation and then back up with the buffer and say, oh, now that we've gotten to the end of the operation, we know what the X min and the X max for that op were, because we were calculating them the whole time. Now we can write that data back to the beginning. So that's kind of the idea that we're doing here. Okay? All right. We've got more to talk about, specifically with this buffer, because I want to go through it and, again, just try and tie in as many of these examples as possible. But we're also coming up on the midpoint of our class. So we are going to get ready and take a half-hour break. That's kind of our mid-class break. Gives you a chance to get some food, hit the restroom, do anything you need to do, kind of middle of class. Before we do that, are there any questions about anything we've covered up until this point? And it's okay if you don't have questions, but I do want to, make sure that we got time to cover them if they do come up. Okay, Bill says no. It's okay. All right. Well, I'm not seeing anybody jump out, and that's fine. That's totally cool. So, tell you what, we'll go ahead and take our mid-class break. It is 3 p.m. now on the East Coast here, so we're going to go ahead and break until 3:30. So I'll see you guys back here at that time. Thanks, everybody.